Okay. So I am about to talk about how we did the study. And I want you all to be cognizant of the fact that this audience is filled of PhD students from MIT and utility experts and dentists. Like, it's a wide range. So please excuse me if I don't address you in particular. And if you have questions afterward, just ask anybody on the team. We're happy to talk. And a peer-reviewed paper hopefully will follow with a lot more science. So once the law passed that these leaks of environmental significance must be repaired, we had a problem because with over 16,000 leaks across the state, no one had ever come up with an easy, reliable, fast method of distinguishing which of these leaks were large volume. The chamber method that Margaret used in her study would not work because it would take way, way too long. So the Department of Public Utilities selected the bar hole method, which is a simple method in which you bang a hole in the ground, insert the nozzle of a combustible gas indicator to read the percent of gas in the ground. If it's over 50% for 2 years in a row, that would be considered a large volume leak. The problem is that no one had ever tested if this method would be a reliable method to find the large volume leaks. So the goal of our study was, first off, test the method. If it worked, fantastic. If it didn't, we had to find some other method to find those large volume leaks. And remember, the potential prize here was big. There's, clearly a wide range of assumptions and information and the time frame of the methane impact that can go into this, but the emissions equivalent is somewhere between 2 and 6% of the state's greenhouse gas emission inventory if we manage to fix all of these large volume leaks. That's basically the equivalent of turning off or decreasing the emissions from our stores and businesses by half. So it's a large amount. We also, because Massachusetts is ahead on this issue, we have a chance of making a national model for this. So before I start about the study, let me say that when you stand on the sidewalk and you smell gas, most people make the assumption that it's one hole in one pipe. That's not necessarily true. Because neighborhoods are built of the same materials at the same time, they tend to be leak-prone infrastructure will congregate. So because of this, we try to think of the leaks as leak locations instead of a leak, because a leak, you always think one hole in one pipe. And it reminds me of the way my mom would always talk about the mouse in her kitchen for years. She had the mouse in the kitchen. And I wanted to say, where there's one mouse. So anyway. These are the leaks we studied. The utilities gave us 69 leaks as selected by the bar hole method. We researchers additionally put into the pile 14 leaks that were selected by the Picaro. I'll explain what that is in a minute. These leaks were on every type of pipe material that's leak prone, from cast iron to bare steel, etc. They covered a wide gamut of operating pressures. The pipes have different operating pressures, everything from ½ pound per square inch pressure all the way up to 99 pounds per square inch. The methods we used are basically, we studied these 83 total leaks in every way we could think of, and then we compared the leak rate in 3 different ways. Once we knew which leaks were the largest volume, we looked for the characteristics that would easily identify those leaks. So pay attention, because at the end you all get to vote on which methods you think were most successful, okay? And the success is determined as by being reliable and easiest. So first, we studied the leaks the way the utilities do.
For every leak in our study, we performed a leak survey. We located the leak using gas detection equipment. Once the leak was located, the FI, or flame ionization unit, determined how far the gas had traveled. We measured the width and the length of this gas-saturated surface area. This is called the leak extent, or footprint. Bar hole reads were also made whenever possible.
Next, we also did this.
We also drove by each leak with a Picaro, a high-precision natural gas analyzer. This device has an intake tube in the front of the car. The Picaro analyzes the air to measure the parts per million of methane, while it maps its location with GPS. The data that results produce maps like these. In order to reduce the effect of the wind and other factors, we drove by each leak at a steady speed multiple times. We located the largest peaks using an algorithm called area under the curve. This is a numerical way to compare the size of different peaks. We wanted to find out if the Picaro could select high-volume leaks.
Okay, and then we compared the leak rate in 3 different ways. First way is...
Every leak in our study was measured using the chamber method. This was the same method used in the Hendricks study. The chamber was placed on every spot with measurable gas escaping. We recorded how quickly the gas built up inside the chamber over time. This was done in order to calculate the flux, or rate of emissions. One leak was so large, we had to make 170 separate chamber placements. The chamber method has been scientifically verified and peer-reviewed. Though considered to be the gold standard of gas measurement, it is extremely laborious. In order to verify each of the other methods of measuring gas, we compared its results to the chamber method data.
So that's the first method, that's the reference method. These are the methods we were testing.
I'm Alan Waxman. I am the founder and chief scientist of Multisensor Scientific. We've built an infrared camera that operates in a part of the infrared spectrum that we call the shortwave infrared. So we're actually looking at reflected sunlight. We're not looking at a heat signature at all. The information is relayed to a user interface on a small commercial tablet.
What I'm particularly excited about is that I see this technology and this product as a win-win-win situation. It's going to help utilities to be more productive, to find leaks faster, to get better quality of data. At the same time, we're going to help the environment to reduce methane emissions.
The camera was only used on national grid leaks, and it's a passive method. This next method I'm going to show you is, the video is a little bit longer because it was invented by the entire coalition, and so it's a beautiful demonstration of what we can all do together. We needed a device to tell us which were the biggest leaks. With a tool like that, utilities could learn how to save the most emissions for the least cost. This is the story of the flux bar. We started off by consulting experts. Luckily, Dan Cody from NiSource began helping us. NiSource is the parent company of Columbia Gas.
First, it had to be a simple process. The equipment had to be rugged. It had to be easy to use. It also had to fit in with the typical flow of a leak repair. It couldn't be disruptive to the crew to get the work done. And at the same time, it had to be as accurate as we could reasonably make it.
Our first designs were very primitive. When we showed this design at a meeting with Eversource, there was this really long silence. Then Kevin Kelly of Eversource suggested we consider the purger instead. It's a utility tool that vacuums gas out from under a street so a leak can be located. If the purger were modified, it might work. So we organized an MIT hackathon to improve it. With input from the hackathon, we approached Brian Ferry of Millibar, the local manufacturer of the purger. He created a prototype that we tested to ensure its accuracy.
Within just 2 months, Millibar had produced the first flux bar. It was tested out for the first time in Springfield with 3 utilities watching. The flux bar works by being inserted into a hole drilled right over the leak. It gently vacuums air out of the ground at a consistent 3 cubic feet per minute. By connecting a gas detection device, we can measure the percent of gas in that consistent airflow. Once the built-up gas under the street is drawn off, the result allows us to measure the leak rate.
That will give us much better insight into not just environmental risks, but also public safety risks that are a core obligation we have as gas operators.
The flux bar can't be used, just to explain, for identification of leaks because it needs a compressor truck in order to work, but it's really easy to use when you're actually just before you repair the leaks. So it's good at verifying the leaks. So those were the 3 ways we used to, check the leak rate. Zainab's going to tell you about after the break about what methods actually worked, but I thought you'd all get, it would be great to have you all vote for a second. Who thinks the bar hole method would be the method, would work to be the easiest and most reliable? Show of hands. Okay. How about leak footprint? Okay. How about the Picaro? Yeah, we got some Picaro. How about the flux bar, number 4? Maybe more flux bar. How about the MSS camera? A lot of MSS camera. Okay, and it's all judged by the, as judged by the chamber method.
Happen. So it's very exciting to be part of this and to reveal some of the results of the study.
Thank you. All right, so I'm really excited to share this, and I have made a big effort, thanks to a lot of feedback from my colleagues, to make it much less technical. So I'm going to kind of try to switch back and forth a little bit and give you a simplified version, and then for those of you who really need to know the R-squared, that's there too. So I'm going to start with, those are my boots. And thank you to Columbia Gas for the electrical tape. But my first conclusion right off is, having gone out in those boots and then the next pair of boots into the street and measured a lot of things and learned a lot of things and listened to a lot of guys who've been doing this for a long time, my biggest general conclusion is that it's not easy. It's not an easy problem. And even from a scientific view, this is actually a genuine multivariate complex system, and therefore it is not easily measured or solved. Oh, okay. Closer to the mic. They don't make podiums for my height. All right. Are we good? All right. So in order to give you an idea of that, I want to actually show you so you understand how complicated it is. So I went to the same leak multiple times. It was in Cambridge, so it was close to me, and measured it in the same way with the same tool day after day. And this little graph is the percent gas on different days. And it varies a lot. And any of the gas guys know, that those bottom zeros are when it's raining. That's easy. But while it's getting wetter, while it's getting drier, there's a lot of factors. And if we add that humidity, well, this was the humidity during that time, so it's tracking in opposition. And then you add the temperature. Ooh, it's kind of going with the gas leak. So when the temperature rises, gas moves faster, right? But the thing is that these are just a few of the variables. There are so many. There's the type of pipe, the pressure, the age, there's a whole bunch of other stuff, the soil porosity. And so you put it all together, and it's a really hard problem to solve. So I want to make sure we start from that. So we threw the kitchen sink at it. We got everything we could get going to solve the problem. And of course, the problem we're trying to solve here is to find out how to find the biggest leaks, to identify them. Audrey has already introduced you to each of these approaches. and clarified that the chamber is what we're using as our reference. So we're going to compare everything to that to see how close we get. So we're going to start by asking, does the bar hole method work? And this is the one that was initially proposed by the DPU, well, by everyone, like, okay, well, maybe we can do it this way. And that is the way we had the utilities select the leaks initially. I'm going to try to do this. So if I took all the leaks and I split them into two piles, one that has a bar hole read of higher than 50%, and the other pile that has a bar hole read of lower than 50%, that ends up a pretty close to equal pile of things, but the emissions, the average emissions of those piles is really close to the same. So it's not choosing bigger leaks by being greater than 50% gas in the bar hole. Put another way, this is comparing one bar hole to the other. And remember that variability and the challenge of measuring the leaks. So here's one that looks just about right. The first bar hole read is around 50%. The second bar hole read is around 50%. It's like, that's good. Okay, so if it all came out like that, you'd get a nice straight line across, and we'd have a perfect correlation, and we go out with our bar hole and say, oh, that's a big one. But they didn't all come out like that. And these are measurements done by utility in the same leak in the same place. So this one is clearly, it was 100%, close to 100%, and then 25% the next time. And if you just fill this in and put a whole bunch of them up there, we had to conclude that at least the way we're doing it now, this isn't going to be a method we can use right away. And that doesn't mean it's not a real measurement. It really is, but it's just the question of what you're measuring. I'm going to do it one more way. This is for the more science inclined. This is a correlation chart between the chamber flux. Remember, flux is not the thing in Back to the Future, but it's actually the emissions of gas coming out of the ground in cubic feet per day, and the bar hole read. And this is not a correlation, R squared 0.03. So we're going to move on and cross off bar hole. Leak footprint method. So this, again, was the area of the extent of the leak on the surface, which is the only thing we can measure unless we dig, right? So we did the same thing, grouping two groups, two piles. So the pile on the right is leaks that are greater than 2,000 square foot footprint. And the one on the left is leaks that are less than 2,000 square foot footprint. The average emissions for those two groups are really different. So you can see pretty clearly from this that choosing leaks that are over 2,000 square feet results in, on average, a bigger leak. Again, switching. R squared of 0.68 is a pretty good correlation. It holds when you take the outliers out as well. There's all kinds of stories in this, but we'll get to that. So yeah, the leak footprint is one way to look at the leaks and say, hey, this one's bigger than that one. And that's really what our goal is to be able to rank order them and take those top ones and fix them fast and put our resources there. So the Picaro, or that area under the curve method that was mentioned before, peak area. We'll actually switch to this. So first of all, we didn't get a strong correlation. There were sensitivity issues between the Picaro area under the curve and the size of the leak by chamber. But we did see something else, and that is that it was actually pretty good at picking large leaks, not at ranking them in order, but at picking out the biggest ones. So I'm comparing here three approaches that we just talked about. So bar hole, selected by bar hole greater than 50%, you get an average flux of under 100. Selected by footprint greater than 2,000, you get an average flux like around 250. And then selected by Picaro, peak area, you actually get a really high average flux. So there is some potential there, but again, we can't rank order using it. All right, so we're giving it a partially. How are we doing so far? Who's winning? Not a lot of people voted for leak footprint. Simple is sometimes the best. All right, so we're doing multi-sensor camera now, and I want to make sure I'm clear that this was a proof of concept, and it was really amazing of National Grid to support that and take that risk as well, outside of all of the collaboration risks. It's very promising, but as a proof of concept, we didn't get everything we wanted yet, but it's coming. And so I'm going to show you, instead of results, I'm going to show you a different kind of result to show you what the potential is. And this is a before photo of the leak, and this is like a live image on a video, or you can take a still. And then during the repair, and you can see the leaks there, and then after. It's like magic, right? So it's a really radically different way of looking at the leak, and they're working really hard to move it to a product to be able to do things like rank order. So we'll see. So we can't, but for right now, hitting the ground, we can't use it yet. So to the future. Okay, that flux bar that everyone put a lot of innovation into together. So to be clear, we take the measurement from the percent gas coming through the flux bar, and we record it over time, and it drops down as you empty out the saved up gas under the ground. And then you get to a steady state or a plateau. And that is the number that we're using as the flux bar measure. So, all right, so if you group them into two categories, again, our piles, if you get a bigger percent gas on the flux bar, you get a bigger leak. We're starting to see how this works, right? And to do it differently, you put it out on a graph and you get a high R value and a correlation that's pretty strong. And we have more data coming in that's holding true. All right, and then the reference. Who voted for the reference for the chamber? Okay, because if you did, you've automatically volunteered yourself to go out and do it next summer. But what you can see really clearly here is we were lucky enough to actually find some real options. It didn't have to come out that way. We could have got nothing. And so moving forward, while the technologies work, we also in the process learned a lot about the leaks. I mean, we learned a lot about everything, but going back to that leak location footprint chart and seeing the couple that are out there, the outliers, there's stories to each of them, but I'm going to pick out those ones that are over 265 because that's the top 7%. Remember the 7%, 50%? All right, so I'm going to take the top 7%, and I'm going to add them up. And they come out to 47% of the methane. And that's true despite the fact that we were looking at cast iron, wrought iron, coated steel, steel, plastic, ranging from ½ pound to 99 pounds per square inch. So that's really, really, really encouraging, and it's some of the best news that we actually can do this. This is possible. I'm going to shift quickly and point out that we're going to keep learning, that part of this process is to continue to learn, and as we refine our understanding of what those large volume leaks look like, we get some information. So here, you can see that the middle pressure leaks tend to be bigger. Now there's probably a story behind that, something like the big ones get fixed faster, or who knows. Less than 20, it's just smaller. It makes sense, but it's also a clue. Another clue or trend is that actually we're losing a lot of methane from bare steel. While cast iron is the first and classic leak-prone pipe, it looks like we have to pay a lot of attention to bare steel too. So, to summarize, the bar hole measures are not consistent and they don't indicate volume. Again, this doesn't mean it can't evolve to be better. Flux bar and leak footprint measures do indicate volume. So they get their little, who won? Anybody? There were a lot of votes for flux bar, so you're good. We also have some emerging identification that the pipe pressure and the pipe material are part of the story. We have also this information that the Picaro or another tool like it, we happen to have a Picaro like Los Gatos, et cetera, has potential to find leaks. And the MSS camera may too in the future. So what does this mean? And I tried a bunch of different ways to try to communicate this. But that 7% is 50% of the methane. So the chamber method gets those 7%, and we get 50% of the methane by fixing them. If we used the bar hole method of greater than 50%, that's how much of the methane we would get in the same effort, the same number of leaks. If we use, for example, the footprint, which we just figured out, which is not as perfect as the chamber, but it's fast, easy, and you won't, you won't kill yourself. You get really close. And the hope is that as we refine and gain feedback back and learn more, for example, getting feedback from the flux bar on ranking, that we can get closer and closer to fixing the most methane fastest with the least effort. So that's it. So I'm going to not go into the details, but man, we spent a lot of time on those details. And this is a shared action plan between the utilities and the environmentalists to move forward on this topic as quickly as we can in a practical way. So we start with identification. Audrey, we're going to have to do a lot of clicking here, sorry. See? So basically, we're switching from bar hole to leak extent. It's a big, simple change. Repair, we're going to click again, sorry. Yep. So there's a lot of details here because it's a complicated process, so there are trade-offs and stuff, but basically the very, very largest ones, they're going to go after in the first year, and the second category, we grouped them into two categories, we prioritized. They're going to go after in 2 years. And that's actually a lot faster than it would have otherwise happened. It doesn't always sound fast. That's actually really fast. Next. Nice, huh? So verification. And this is part of where we just started this journey, and we need to get feedback. So they want to know if this is working, and we want to know if it's working too. So we're going to check some of the leaks with the flux bar to have another way of checking if we're ranking them as correctly as large leaks. And of course, they already report to the DPU, but this will be added, the leak extent. So if you can keep clicking, Audrey, sorry. Yeah, there we go. Reassessment. So again, with the idea of an evolution and ongoing learning, a group will get together and reassess the situation annually for the first couple of years so that we keep evolving fast. And hopefully, like they described with the leak-prone pipe, this is a temporary challenge, I very much hope. And we're trying to just prioritize and get the returns quickly. And finally, they're stuck with us for the next year at least now. We're going to keep collaborating to provide support around some of the data analysis in the first year so that we can see how it comes out, because we're kind of dying to know.
Thank you.